Okay, so in your lab book, lab number 4, capacitive reactance. So what does it tell you to do here in this lab? So you make the model of your function generator and your oscilloscope, and if you have a serial number, you don't have to fill that out, just the model is fine. And then you go and you get each of these. You might already have the 10K ohm, I do not know. You need a 1 and a 2.2 microfarad capacitor. Okay, so this is the schematic that you set up. You set up your voltage supply, which is your signal generator. This is your signal generator. If you haven't used a signal generator before, this is where you're going to start doing that. You enter in 10 volts peak to peak, and assuming that the reactance of the capacitor is much smaller than 10K, can be ignored, and determine the circulating current using measured components values and record in table 4.1. Okay, now I just went across the generator and went across the capacitor. So this is you can look at the so so this is your one of the things that he does that is kind of he gets calculate the theoretical value exit using the measured capacitor value and record in table 4.2. So that's the theoretical. Now the okay, so right up here is where it's assuming that the reactance of the capacitor is much smaller than 10K and can be ignored. Okay, determine the circulating current using the measured component values and record. So you take V peak and divide by R 10K, and that is your I. Okay, that is not exact, but it is an approximation that you can use, and that's why he says this. And I'm going to go through this with you, but that's the key, in my opinion, to this lab. It's so we're going through this lab so that you can have a little bit of an idea ahead of time what is going on. And I will be there for a while, but I said we're going to dismiss the lecture at 9 o'clock. And if I go past 9, somebody please raise their hand and say it's time to go. So I'll dismiss you at 9 to go to the lab, and then as soon as you get there, I'll show you what I would use for the connections to the voltage generator and the oscilloscope, and those are the things you should use for your. That's how you should hook the circuit up, okay? But I'll show you that in the lab. But the key to this is this part right here, where you can say, now here, it looks like everything is going to be measured in peak to peak values. So you've got to be careful, but he's saying 10 volts peak to peak, which should be 5 volts peak, which would be about 3.3 volts RMS. So you don't worry about that. we're not going to use the voltmeter and measure the RMS values today. We're going to be measuring everything based on the height of the signal, okay? So you're going to key in on the signal generator, 10 volts peak to peak, and that's going to be the value that you're going to use. So 10 volts peak to peak, and then you're going to go run that through a 10K resistor, and that's going to give you your I, because he's saying that the reactance of the capacitor is much smaller than 10K and can be ignored. So in this circuit, how do you get your I is based on this over this. You can effectively ignore this. Does that make sense? So that once you get the V you measure the V across this, okay? The voltage across the capacitor is equal to something, okay? Whatever. And then what is your experimental X sub C is equal to that value divided by I, which is calculated from right there. It's not right, it's not exact, but it's what you do in this lab. Okay? Does that make sense? Because the value of I is not affected much by the value of the impedance of X sub C. So the X sub C values are always going to be much less than 10K ohms. All right? But you're going to see that X sub C number go down as you go up in frequency. Why? X sub C is equal to what? Minus J, but you can effectively ignore this today. Okay, you can ignore it. Sometimes you can, sometimes you can't, but today, but there's a J in there. I know, but you can ignore it. So it's really 2 pi FC. Okay, so you pick a C, it's a constant, but the F, as you go up, what happens to the value of the as F goes up, X sub C goes down. Easy, okay? Does that make sense? That's the key to this whole thing. You can effectively ignore the impedance of the X sub C for calculating I. That's what that means. It makes this lab very doable, and you can, I hate to use the word zip right through it, but you can. But that's basically what is going on here. And until you get that in your head, it's confusing. Like, boy, how can you get X sub C? How can you get X sub C theoretical? Or not? How can you get X sub C theoretical because you don't know, or not theoretical. The X sub C theoretical is 1 over 2 pi FC. So at each point you have to calculate that and measure that. So the theoretical value is this, but the practical value is the measured value of voltage across the capacitor divided by that I, which is this right here. Okay? Now, as long as everything is measured in peak to peak, you're good. If I is in peak to peak, excuse me, no, yeah. See, this would be I peak to peak. If you measured everything peak to peak, this gives you your X sub C. If all of a sudden you flip to the peak value, then if you're measuring peak to peak everywhere, you're good. But you've got to measure it across the board, everything peak to peak, or if you go to just peak, if it asks you just for peak, you got to do it that way. So you cannot ignore this peak to peak thing anymore. So here's I source peak to peak, and here's your various frequencies, blah, 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 for your one resistor, for your one, and here's for your other one, and then you answer a few questions, do a real short conclusion, a couple of sentences. I see now that X sub C goes higher, or goes lower at a higher frequency. I see it in my, I see that. Frequency changes the resistance of a capacitor. And it does. What are the units of X sub C? Ohms. But there's a J in front of it, really, but we can ignore it. So when can you ignore? When can you not ignore? A good question. You can kind of ignore it today in this lab. The J kind of goes away. You don't have to. You don't have to worry about J in this lab. Usually you do. Today you don't. You got to on lab or in exams and math. When you're doing math, you have to ignore it. But today, for the lab, you can kind of ignore it, and that's what he's saying. Any questions about this? Okay. The other thing is, have you ever used a signal generator before? Have you used it before? You've seen a signal generator. You know how to use it. Okay. So again, the best leads for the signal generator and then the best leads for the scope are not the same leads. I want to show you which I would prefer you use for that. And you say, well, can you get it to work otherwise? Yes, you probably can. You can probably use a scope lead for your generator leads, but don't. And don't use, and definitely don't use a generator lead for a scope lead. It will not work. You can hook it up, but you can make it look right, but it doesn't give you, usually doesn't give you good values, okay? And the other thing about these labs is this. Expect high deviations. Don't expect 1 or 2% deviations. Expect 20, 30% deviations. Now, if you get 100% deviation, or if you get 70 or 80%, you did something wrong. But don't expect 0 or 5 or 10% deviations. Expect a number that is 20, 30%. Now, if you get 10%, fantastic. But don't criticize yourself and don't go back and beat yourself up if you don't get it. If you get 20%, that's just the way it is today. And these are not as exact as you did in resistive circuits. Everybody understand? Resistive circuits, you could nail it. You get 5% or 3%, and you were, oh, that's, good. But today, we flipped over into capacitors and inductors, and it does not work as well. You cannot get numbers that are exact. Okay? All right. That's it. Any questions anybody's got on the lab? Well, I'm going to go through some of the problems at the end of chapter 3. I'm just going to jump to the end of chapter 3 because, it's not that I'm in a hurry, but I really do think that that's the best way to get through some of this stuff is to just, do it and say, we're moving through the simpler part of this. There is a quiz I can give you, so be aware of that. I probably will give you something. Okay. Okay, so problems in chapter 3. I'm going to work a few of them. You have some of these assigned. Who's going to win the Super Bowl? Any ideas? Anybody care? Seahawks? I think so. I don't know. I'm going to be driving a truck back from Illinois and listening to it on the way back, so it's kind of a But anyway. Anybody see last night Illinois Northwestern? Did anybody see how that game ended? No. I was watching about halfway through, and they had 3 times the points. It was 60-20, 60-23 at one point. So again, fell asleep. I was watching something else and so, um, you don't have to watch what I watch, but I usually watch Big Ten, but oh my goodness, this is gonna be a year for, watching this stuff because they got Illinois's got the people, they got see, Northwestern and the state of Illinois, they're the upper crust, and everybody else goes to the University of Illinois. Not everybody, but that's it's kind of like it's not Ohio State versus U Toledo, but I guess it would be like Case Western or something, there. But anyway, Northwestern is the up here, and then everybody else. Like to see it. Oh well. So, what is the effective impedance in number 5 right there? How do you find the effective impedance of that circuit? This gets a little bit more tacky, doesn't it? Okay, so what is the effective impedance? The Z, you call it Z effective or just Z for this circuit. So this, see, for number 5, okay? 3.5. How do you find it? AJ, how do you find it for this circuit? They give you the impedances for each individual item. But what is the in polar? How do you find it? Okay, it's the 1/1 rule. You mean you've got to use 1/1 with J's? Yeah. That's why I told you to get a calculator that does this. So this is what you do, all right? So now it is 1/1 J 200 plus 1/300 plus 1 over minus J 1500. How do you find it? Menu, on menu complex equals, okay? That's how you start. 1 divided by parenthesis 1 divided by 200i plus 1 divided by 300 plus 1 divided by minus 1500i parenthesis equals. And then you get it in rectangular, option down 1 equals, and then you get the answer. What is the answer? You got to be able to do this. This is not negotiable. You've got to be able to do this. 182.913 at angle 52.43 degrees. You got to be able to do this, okay? Now I ordered 2 calculators. One is already committed. I've got one more that I will give to somebody if they come and see me, or they won't. If they say, I just can't find this calculator. The university bought 2 of them. I didn't buy them, the university bought them. They're coming later today. I'll have them this afternoon. You got my phone number. Text me before 2:30. Between noon and 2:30, I should have them. And then at 2:30, I go teach my class. At 3:45 or 4 o'clock, I'm done. I usually just go home at that point in time. I'm not coming back tomorrow. Going to Illinois. So if you are interested in one of those calculators and you don't have one of these calculators, I got one left. And if 2 people come to me, I'll order some more. But after the discussion on Tuesday, I went ahead and placed an order for 2 of them. And they're $28 a piece. They're not going to break the bank. I'm not worried about it. The university can cough that up, okay? $56, done. But I ordered 2, one's committed, one's not. So if you are in that position where you say, I might, now that he's talking about stuff like this, I need that calculator. Yes, you do. If you can't get this quickly, you're in deep doo-doo right now in this course, okay? I've been talking about it. Now here it is. Okay. Anybody not be able to get that? You don't have to admit, you don't have to hold your hand up, but you should be able to get this. All right. The time has come. Okay. You got to do this. Number 6. Again, they go back and do this. If the frequency is halved, what happens? If you have the frequency, what happens to this one? Number 6. If you have the frequency, the F is in the numerator, right? So if you have the frequency, you have the impedance. So you basically, here, it is J100. The 300 stays as is. If you have the frequency here, if you take the denominator and divide it by 2, what happens? It goes up. So this would be a minus J3K. Any questions? So if you have the frequency, F over 2, you get this. If you double it, you go the other way. I'm not going to do those again, okay? But that's how that's done. Oh, by the way, if you were to do this, what would be the Z? I'll give it to you. I'll give you the answer that I got. It's 97.29 at an angle 70.97. And if you do the other way, which is F times 2, it's J400. Keep the 300. And it's minus J750. Bless you. Minus J750, that's a 7. What would it be then? It's Z is equal to 283.15 at angle 19.29. Okay, any questions, any comments? Everybody see what I just did? Please don't just sit there and say, he doesn't really mean this. I mean, this is what you got to be able to do. Okay? Please be able to do this. If not today, by next Tuesday. Okay? I'm giving you the weekend. But this is how you do this stuff. And if you can't get it, come and see me because we'll practice it. But you've got to have a calculator like this or I just won't. Only 28 bucks. They're not the end of the world. Okay? All right, determine the frequency below which the impedance is mostly resistive, blah, 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 and all that kind of stuff. Forget about it. Okay, I'm not going to ask that question. Okay, maybe, number 7. So here you've got a, number 7, you've got a question for, again, I don't typically ask this kind of question, but this is number 7, 3.7. Go back to the circuit right here. 75, and you've got a 47 picofarads, okay? So now you're asking the question, when does 75 equal 1 over 2 pi fc? Okay? And C is 47 times 10 to the minus 12th. At what point do you get that answer? It's when F is greater than 45 megahertz. That's how that's done. When they say when it is greater, what do? You don't use the greater than, you use the equal sign, and then you say at the end you play the trick and say, here's the teeter-totter. At what point does it tip this way? Well, it tips this way after it goes through the equal sign. Okay, so you use the equal sign and then you solve it this way, and then you say when it is greater than that, then it is This is when it's equal. This is the midpoint of the teeter-totter right there. Okay, that's number 7. Any questions about that one? You play the game of greater than by using the equal sign. And then you go back and you figure out which way it tips, and that's how you do that. Okay, and number 8, same song, second verse. It's the same thing, and it's 5.09 hertz. 16 is equal to 2 pi f times 500 millihenries. F is equal to 5.09 Hz. Now, is there such a thing as 5.09 hertz? Yes, there is. It's a very slow boat. That means it oscillates 5 times a second. But it's possible. Okay. Number 13. Determine the 4 branch currents. Okay, so this is the kind of question, this is, as they say, this is a good test question. Okay, so how do you build a test in a course like this? You take 1 problem or 2 problems from each chapter, and this would be the star question from chapter 3 right here. Okay, what are the 4 currents? Well, you've got the current through the capacitor, you got the current through the resistor, you got the current through the inductor. You got here, you got here, you got here, and you got here. Okay? Now, what is the current through the capacitor? It's 10 volts peak to peak. And again, now we're talking about what? Everything in this, the answer and everything in this problem is in peak to peak. Because once you name peak to peak as your starting point, everything becomes peak to peak. So you use the 10 and forget about it, and at the end you put the I peak to peak back in. Okay, does that make sense? Because your answers and everything are now going to be in peak to peak. Okay, so use the 10, forget about the idea of peak to peak, but at the end you come back and put them all in. Okay, so this is not a big deal. So use 10 divided by what? Minus J5K. That's my IC, right? What is that? J2 milliamps. What is my IR? 10 divided by 2K is my IR. Is equal to what? 5 milliamps. My IC, or my IL, excuse me, my IL is equal to what? 10 divided by J1K, which is equal to minus J10 milliamps. Now, how do you add these together? You don't just add them as numbers, do you? You add them as polar numbers. So what you do, this current right here is I total, this is I total is equal to the sum of the 3. But how do you do that? Complex mode, boom, splat, done. Okay, does everybody follow that? What is the number for 13? It's 2. You can use everything in milliamps, so forget about the 0.002, just say everything is in milliamps. So it is 2I plus 5 minus 10I equals, what's your answer? It's not 2 plus 5 plus 10, it's not that. Or 2 plus 5 minus 10, it is not that. What is it? It's a polar number. It's 9.43 at angle minus 57.99 milliamps. Peak to peak. Yes, sir?
Why did the inductors hurt?
So when you move the J to the numerator, it becomes a minus J. Okay? A J in the denominator becomes a minus J in the numerator. That's all it is. Okay. Any questions about number 13? That makes sense. By the way, is this the same problem you worked in resistive circuits? Yeah, exactly the same problem. Except for what? Stupid complex numbers. They're not stupid. They explain physical phenomenon, but that's what you've got, okay? Any questions about number 13? Number 16. Okay, this is the same thing, except they just drew the circuit funny, didn't they? So now they said it's 2 volts peak, so now all your answers are going to be in peak. Okay? Any questions about that? And they drew the circuit weird. But other than that, my tendency is to not follow their weirdness. I just do it like we've always done it. Put it over here on the left, and then put the 3 that are in parallel, the resistor, the capacitor, and the inductor. Boom, splat, done. Okay? Find the 3 currents. What are they? In this case, I don't really care what the individual ones are. Oh, yes, I do. I'm just going to say it's 2 milliamps through the resistor plus J 1 milliamp through the capacitor minus J 0.67 milliamps through the inductor, which is equal to what? 2.027 at angle 9.369 degrees. So that is my I peak. Not peak to peak, because they gave you the starting point. It's how they give you the starting point is how you answer the question. So it's 2 volts peak. So now you've got this. Any questions about number 16? Please be able to get these answers. If you cannot crank through and get these answers, and this is going to be posted, this will be on the web. Do you understand that you can go back if you're not understanding this? You have the opportunity to go back and work through this again by looking at starting and stopping the video until you get it, because you practice this and practice it until you get it, because this is not optional. These are questions that you must be able to crank through. I mean, not the word must, but if you're to get an A in this course, you must be able to do this. How's that? Does that make sense? Because that's exactly the status of where we're at. Number 23. This is a what? What is this? Okay, so now we don't have the option of V over X or V over R. We have to now do what first? For this one, we have to do what first? Number 23. What must you do first if you have current? Now you have really 2 options. You can take the current and, because it's in parallel with a resistor, and you can do this to it, okay? So you can play this game, and this works, by the way. Okay? So you can do this. Take the 2.2K, move them over to the left, and then turn it into a voltage supply with V here is equal to I times R, and then put the resistor up here. So this I and this R become this and this. Why is that? It's called Thevenin. You Thevenize it, and that works. What's the other way? That way, then you attack this problem just the way you attacked all the other problems. except for the fact that it's going to be kind of hard to find the current through the 2.2K because it's not there anymore like it was. But you can do that. The other way, which is probably the best way, is to find, for this circuit, 2.2K minus J200, J300, and 4.7K. Find the Z total for that. How do you do that? 1 over 2.2 plus 1 over minus J200 plus 1 over J300 plus 1 over 4.7K. This is in K. Because I've got 200 and 300, I've got to put these in K. There, you get it. That's how you do it. Okay, what would that be? Z total is 212.127 at angle minus 81.86. Now, what is voltage across this circuit? What is the voltage across this circuit? V equals I times Z. So here's your I, 20 milliamps. Here's your Z. And there's your voltage. Voltage is equal to 4.24 at angle minus 87.86. Now the I across each of the components is V divided by that one. I total, excuse me, when you get to this point, you cracked it. What is the I through the 2.2K? It's 4.24 over 2.2K. What is the I through the capacitor? It's 4.24 over minus J200. What is the I through the J300? It's 4.24 divided by J300. What is the I through the 4.7K? It's 4.24 divided by 4.7K. Does everybody follow that? That's it. That's all it is. This is the preferred way to go. I do not like this approach, but it kind of works. It does work, but you know, I forget about this approach for this one. Do it this way. Will he ask a current question? Maybe. Maybe one. Tend to ask voltage questions, might ask one current question. You got to turn it into voltage. So you got to do this step first, and then find voltage, and then go from there. Okay? You got to get to this point where you can find voltage. Okay, 25. Got two more to do. We're close to getting through this. I'm going to write out the quiz for you. I'm going to tell you what it is, but I'll tell you in a minute what I'm going to actually assign for you. Okay, now this is another one. Oh my goodness, this has got two current sources in them. What do you do with that? And they're out of phase with each other. So what do you do? For 25, you add I1 and plus I2 vectorially. So what is I? Well, it's 1 milliamp plus it's that. And that's not a bad number. That's 1 plus 2 at angle 90. Can you deal with that? Yes, you can. What's Z total? What it was before, 598.92 at angle minus 3.433 degrees. So what is V across this circuit? V total, or just V, is equal to what? I total times Z, or 1.339 at 60 degrees. So now what is I across the capacitor? What is I across the inductor? V over the X sub C, V over the X sub L, which is in this case 0.669 milliamps at 150 degrees. This one is equal to 0.5356 at minus 30 degrees. Okay, number 27, and then we're done with the problems. Here in 27, you've got one going one way and one going the other. What do? You subtract them. So you've got one going up and one going down. You subtract them. One is at 2 going up. One is at 0.5 angle 45 going down. So you say 2 minus 0.5 at angle 45. That is my I. My I is equal to 2 minus 0.5 at 45 because one's going up, one's going down. Easy peasy. So what is I? You just write it in as that. What is my V? I got to find my Z total. Is equal to 4.961 at angle, this is a weird one, at angle 7.125. So that's my Z total of all these components. This and this and this, 4.961 at angle 7.125. That's your 1 over 1 over rule, okay? Now, your V is equal to I times Z is equal to 2 minus 0.5 at angle 45 times Z, and that's equal to 8.354 at angle minus 4.994. What is my IC? Equal to V over X sub C, which is equal to 0.8354 at angle minus 85 degrees, or 85, and this is in amps. I sub R is equal to that divided by 5, V divided by 5, 1.6708 at angle 4.9 something. And I sub L is equal to 8.358, my voltage divided by J8, which is equal to 1.044 at angle minus 85 something. Any questions? Any comments? Oh my goodness. Will he ask one like that? I don't know. But I could. They're all legal. Those are all legal questions I could ask. So that gets you through that. Okay, so now this is, I'm going to send you this, but the quiz for quiz 3 will be from chapter 2, number 2.15 and 2.44. And we're on to chapter 4, which I'm not going to start today because whatever. But now you got the basis for this whole course. This is, like I said, this course you can teach in 2 weeks if everybody kind of just climbs on board and gets a calculator that they can use, because you've already done all this stuff. Is there anything in this course other than the J, other than the I, that you haven't done in this course, that you haven't already done? Everything that you've done here, you've done before. It's just you didn't do it with eyes. You did it without. You did it with plain numbers. Now you're doing it with complex numbers. Nothing that you did before is any different today, except that you now have, every once in a while, you got an I in there. Not all the time, but you do have them in there. So, any questions anybody's got? I'll send you a text that reminds you that that's your quiz, but that's what your quiz is going to be. Any questions or thoughts? Heaven help us, right? Anybody totally, you don't have to. I understand if you think this is just not what you want to do, but that's why I showed you at the early part of this course. And you can't really say that there's a direct parallel between what we talked about today and this guy. But this is your project at the end. So we basically, at the end of the course, we have lectures, and up until now, the lectures are kind of, at the end of the course, I've kind of struggled. But with this course now, I'm going to go into the actual circuits that we have with we're going to have a little bit of the electronics course in this course, just a little bit to get you started, to get your appetite whetted for that. The 2010 course, we'll do a little bit. Not a lot, but a little bit. But this is an automation project. This is kind of like a mini capstone course. In other words, in your freshman year, you don't expect a person to be able to do a capstone. You will struggle. Everybody does. But that's why we give you 4 weeks. Okay? But the goal is to make this thing, it goes out and comes back. You put 24 volts on this, it goes out. It goes to an end and it stops with the limit switch. Then you flip the leads around and you take the 24 on the other side, and you flip the leads to the 24 volt supply, and what does it do? It goes the other way. So I want you to automate this so it goes out and back and out and back and out and back. And this keeps doing that as long as I put power to it. That's what I want you to do. And with a little time delay at the end, and you don't go to the end of stroke, you go to a little point before that where you set a limit switch. So you don't go to the full stroke, you go a little less than, and you come back to a little less than the full stroke. So again, you put a limit switch at each end. You have to do a little soldering. Oh, it's a little of a lot of stuff. You have to put a breadboard together and put that so it goes back and forth and back and forth and back and forth and back and forth. Then, after you get that up and working and show it to me working, then you take it and you rewire it and put it on a PLC. And in very short order, you have it working again. So what took you about 3 weeks to do with wiring of relays, now you can do in about 30 minutes with the program controller. Okay, but this is the device you're going to be using. Called a linear actuator is all it is. Okay, used to lift things and you lift chairs and open and close windows, open and close doors. Like if you have a cottage or something like that, and you want to open a window at a certain time of the day or whatever, at a certain temperature, it'll open the window a certain amount. Used on greenhouses for opening and closing of the top. Anyways, linear actuator. Used in automation. I think 1 or 2 people still came in, so I don't know who all came in, but I've got the lab here. I think 1 did. Anybody else? Lab. I'm gonna shut this down. I'll see you over in 2380. And like I said, I'm gonna be having to go early, but I want to get you started so that you're well prepared. You don't have to worry about asking me stuff after I leave, is what the point is. So I'll leave a little after 10:05 or 10:10, and I'll see you over there in about 5 minutes, okay? Take care. Thank you.
In chapter 8 and 9, you'll have them graded.
I missed it, so yeah, I'll take it. I'll get it. Thank you. Thank you.